Okay, so I need help here. Someone help me out. Vinay, can you help me out with that first one? The square root of negative 54. How are we going to rewrite that?
You take out like the 9, so put 3 on the outside.
Okay, so I'm going to break this up then into the square root of negative 1 times the square root of 9 times the square root of 6. I think that's what you're saying.
Yeah.
And then we know that's the I up front and then the 3. So we get 3I root 6. Okay, and then what?
And then do the same thing for the other one, but this time we'll do it by like 4.
Okay. 4 times what?
18.
4 times 18. Okay. And then that can simplify some more, right?
Yeah, do it 9.
Okay, and this is square root of 9 times the square root of 2. Okay, so that gives us, this gives us I times 2 times 3 times the square root of 2. So 6I root 2.
Yeah. And then same thing on the other side, we'll take out the 4. So like, yeah.
Square root of 4, square root of 2. And then we have this 3 out front.
Multiply against it.
Okay, so this is I times 2, square root of 2. We've got to multiply that. So we get 6I root 2. Okay, so this is subtracting.
So then cancels out.
That cancels.
And you just have like the first one.
Yeah, and so your final answer was just this. Did everybody get that? Great. Good, good. Okay. And then okay. Chloe, can you help me with factoring the letter B?
It's 2x plus 3
And then x minus 4 equals 0. Okay, so then we set each of those factors equal to 0. So we get that x is equal to negative 3 halves and x is equal to 4. Looks good. All right, questions on either of those? Okay, awesome. Good work. We are going to go back, excuse me, and refer to this second question here again in a minute. So that's part of the reason why I asked you to do that. Definitely need practice with factoring, but I've got something I want to show you with that too. Okay, so that's why I asked you to do that one. All right, so this rational zero theorem, I need to kind of explain a little bit about this. What this theorem tells us, it gives us a way to kind of think about or figure out what possible zeros we could have based on what we see here. So I will tell you that most textbooks or resources that you see, so on down the road in the future, you definitely need to be familiar with this being referred to as P over Q. That's how most textbooks refer to this. But I'm going to ask you to think about it in terms of C over LC. I think it's easier to remember because it gets confusing thinking about what P and Q are. So what this is saying, what this theorem tells us is that in order to figure out what all of the different possible rational zeros are that we could have, we want to look at the factors of the constant. That's what the C stands for, is constant. So factors of the constant, and then we want to write this as a ratio, so we're going to put them over all of the factors of the leading coefficient. So that's what the LC stands for, factors of leading. I'm trying to write and talk at the same time. It's not working well. So C for constant over leading coefficient, LC for leading coefficient. So we want to look for all of the factors of the constant over the factors of the leading coefficient. What I need you to think about, what I want you to notice is that even when we do our basic factoring for something that's quadratic, our answers are going to have that, right? If we go back and look at, I'm going to color code this also. I'm going to use C, orange for this constant. I'll use blue for the leading coefficient there. Okay, so if we go back and we look at these two answers that we got for this factoring problem that we did where we're solving, I want you to look at the numbers that are in the numerator, right? And those are numbers that were factors of that last term, the constant, right? And then in the denominator, this 2 is coming from being a factor of this leading coefficient. So that's kind of where those numbers are kind of coming from as possibilities, right? We figured out that these are the right ones. Technically, this is over 1, and 1 is a factor of that leading coefficient of 2 also. So even with our basic quadratics where we are factoring, we see this, right? We just didn't ever really talk about it that way. But we can write a list of all of the possible rational zeros by making this list. Factors of the constant over factors of the leading coefficient, okay? So, quick story, way back when in the dinosaur age when I was in high school and I didn't have that graphing calculator at my disposal, we had to count on using all of these factors of the constant over the leading coefficient in order to figure out how to factor or solve and find all of the solutions for this. So I did a lot of synthetic division. So I would have to look at all of these different factors and decide, okay, I'm going to try this, I'm going to try this, I'm going to try this. We luckily now have the beauty of that graphing calculator where we can plug it in and we can find one place where it is actually crossing the x-axis, and then we can kind of work from there. So I'll show you how that works here in just a second. But for now, we're just doing a list of all of the, when you see list all of the possible rational zeros, then that's saying make this list of all of the factors of the constant. So in this case, what is the constant here? What number? Alice, what's the constant in this polynomial? -3. There you go. So the 3 there at the end is the constant, and then the leading coefficient, Alice, is the 4. Okay. So in the numerator, we need to think of all of the factors of 3. So in the numerator, we would have 1 and 3. In the denominator, all of the factors of 4. So think about that. That's going to be 1 and 2 and 4. Only now we've got to write this as a list because we also have to consider, I want to put each of these numbers over in the numerator over each of the numbers in the denominator. So this is saying I want to consider positive and -1 and positive and -3. I need to consider the positive and -1 over 2, positive and -3 over 2. And then I need to consider positive 1 over 4 and positive and -3 over 4. So from making our list of what the factors are, then we can make the full list of, here are all of the possible rational zeros. Okay, so like I said, from here, for me back in the dinosaur age, I had to just try one of those numbers. I had to do synthetic division. I put positive 1 in there and I'd do synthetic division to see if it divided evenly. If it worked, great, I could move on to my reduced polynomial. If it didn't, then I had to try -1. If that didn't work, I had to try +3 and then -3 and so on. So I had to work through that list. So that's part of the reason why they're asking for this. They just because it was kind of convention. But that's not really the main reason why they're asking. They're wanting you to think about the relationship because there is a relationship there. And this is the more important reason why I still ask you to do this. And that is, I want you to see that relationship between these two numbers because that's an important relationship too. Okay? All right, so try this next one for yourself, where it says list all the possible rational zeros. So you're going to do your list of factors of C over factors of LC and then write out your list. Okay, so Eden, can you give me the list here of all of the possible rational zeros?
So like remove the fraction thing.
Okay,
I wrote 1 and 5, and then as the denominator, I wrote 1 and 2.
okay, so 1 and, whoops, I'm not in writing mode. 1 and 5 in the numerator, and then 1 and 2, oops, oh my gosh. I'm trying to write fast, it's not working well. Okay, so give me the whole list.
Plus or minus 1,
Yep,
plus or minus 5,
plus or minus 5,
plus or minus 1 half, and then plus or minus 5 over 2.
and then plus or minus 5 over 2. Beautiful. Okay. Questions on that? It's pretty straightforward. Okay. Okay. So here's where we're headed with all of this. What I like about this section, what stresses you guys out a little bit, is that now we're going to take a whole bunch of the topics that we've been talking about over the last couple of sections, and we're going to kind of put it all together. So you weren't just learning synthetic division to do synthetic division just that. You learned synthetic division and practiced with that so that now you can use that to do more, right? So some of these questions are truly just this straight, just this blunt. Find all of the zeros. I added in the little note. We're going to start by looking on the graphing calculator. So go ahead and plug this into your calculator. You're not plugging in the f of x, just this function. Go ahead and plug that into your graphing calculator for a sec. Is that right? They're not right on a hash mark. So it's crossing right at 2, but the other points it's not crossing right at a nice pretty hash mark. Okay, so that's one of the zeros that we know we definitely want to use, right? So we're going to use 2, and we're going to do our synthetic division. We have all of the decreasing powers of degree that we need. So 1 and 1 and -5 and -2. So let's do our synthetic division here. And we should get 0, right? If I hadn't gotten 0, I know something's wrong. Okay, so here's why you can't tell where those other graphs crossing exactly, because if you look at what our reduced polynomial is, because we're trying to solve here, if you look at that reduced polynomial, we cannot factor that, which means it's not going to be nice, pretty integers. God bless you. It means we've got to go, to solve this, we've got to go to quadratic formula. So let's plug in. So Emily, can you help me with that?
Yeah, so, like, with the, okay,
So quadratic formula, so opposite of b
so.
is going to be,
3
yep,
plus or minus
yep,
the
square root of,
3 squared,
okay, so 9 minus,
4 times, 1 and 1, so just 1.
okay, all over 2a, which is just going to be 2.
Yeah.
Awesome. Okay, so -3 plus or minus 9 minus 4, so the square root of 5 all over 2. So that's why those other values that you see there, they don't look very pretty because it's a weird kind of irrational number there, right? Remember that means -3 plus root 5 all over 2, -3 minus root 5 all over 2. So all of our zeros, we also want to make sure we remember to include, what did we divide by to begin with? 2. So here's all of our solutions. Okay. All right. Reminder, we've talked about this already a little bit. Here's some properties here. If a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. In other words, if I tell you that we have something that is a degree of 3, then we know we have to have 3 roots or zeros or solutions. Some of them might be real, some of them might be imaginary. We'll talk more about that next week. If I tell you that the degree is 5, how many roots are we going to have? 5 roots, right? Whatever the degree is, that's how many answers we have to have. That's how many solutions we have to have. All right, that's one reminder. And then remember, these come in complex conjugate pairs. I'm going to write that down here at the bottom. Complex conjugate pairs, right? So what it's saying is if a plus bi is a root or a solution or a zero, then a minus bi is also. Remember, that's our complex conjugate. So a plus bi, a minus bi. Whatever the first sign is, it stays the same. We switch the sign for the second one. Okay? So here's how we use this information. We're going to jump ahead a little bit, and then we'll go back and do that other one. I've kind of got those in a weird order. I forgot about that. So we're going to jump down here for a quick sec. It says, find a third degree polynomial function with real coefficients that has -3 is a 0, and so is x equals I. That's what that's saying, right? -3 is a 0, and so is x equals I. If x equals I is a solution, what else is a solution? X equals... No, think complex conjugates. Negative I, exactly. So it's not explicitly stated there, but you have to know and you have to remember to say, okay, I is a solution. That means negative I is also a solution. We have to remember to include both of those. Okay? All right. We're basically working backwards. This question is asking us to work backwards. We have the zeros. Now we need to write these as factors. And we want to multiply this all together and figure out what the polynomial is. Okay? So it is always going to be best and easiest, because you know a trick about multiplying when you're multiplying the conjugates. So we want to do that shortcut if we can, right? Way back a couple sections ago, we talked about multiplying the conjugates together. If we have x minus I times x plus I, our answer, remember, is of the form a squared plus b squared. So if you have to FOIL it out, do that for sure. But if we do a squared, that's going to give us x squared plus, if we do I and negative I, right, that gives us negative I squared, which becomes a plus 1. But now I need to multiply that times this x plus 3. Okay, so let's FOIL this out. Someone help me with that. Eden, can you help me with that? If I multiply the first terms, what am I going to get? Yep, x cubed. And then outside? Yep, plus x. And then inside? And then last, plus 3. So that's my polynomial function. Okay, do you see that? We just worked totally backwards on that. We've been asked, that most of the time we've been getting asked to find the solutions, but now we're saying we have the solutions and we're going to work backwards and multiply to get our polynomial. Try this next one yourselves. Think about how I set this up. I have -3i, so think about what else is a solution, and 5i, think about what else is a solution. Okay, so if x equals -3i is a solution, then we know 3i is a solution. If x equals 5i is a solution, we know -5i. So then we get all of those factors. Now you're definitely don't get your x plus 3i's and your x minus 5i's put together to try to FOIL, because that's gonna get messy. You definitely wanna do your x plus 3i, x minus 3i, multiply that, x plus 5i, x minus 5i, multiply that, and then FOIL those other two. Okay? We did well on that, we got that? Okay. We are not going to worry about that, but we are going to scoot up to the top here So this is the other type of problem, and I put that little reminder there again as well. So go ahead and grab your graphing calculators. Don't put the equal 0, just put in this whole function into your calculator, and then let's take a look. Okay, so a couple of questions. What does the graph look like? It looks like a really tight, skinny parabola, doesn't it? Okay. What's the degree of this polynomial? Look at what the degree here of this polynomial is. The degree is how much? 4. So how many solutions do we need? 4. Okay. It looks like a parabola. It's touching right at the x-axis. That's a bounce. What does that bounce mean? How many times is that particular where is it bouncing? At what value? Where?
0.
Well, it's at the x-axis, but I mean, it's touching the x-axis, but at what x value? At 1. But it's bouncing there. So guys, think about what that means. That means that it's a solution 2 times. So we've got 2 of the solutions. It means we're going to do our division with the number 1 in it. We're going to do that twice. We're going to do the division, get our reduced polynomial. We're going to divide again. So you have to remember and recognize that if you see a bounce like that, that's telling you divide a second time by that. And typically that's kind of the thing that you're going to see. If we're to the 4th power, think about that. We need to be able to divide. We need to be able to divide again so that we get a reduced polynomial that's an x squared, so that then we can do what we know how to do with quadratics, right? Okay, so here's our coefficients. Okay, and I better get 0 when I do this division. If I don't, I know I've done something wrong. Blah, brain freeze. Okay. Okay, I got 0. Now I'm going to do synthetic division again, and I'm going to do that on this reduced polynomial. I'm not going to go back to the original again, or I'd get right back to where I was. I want to reduce again. So 1 what did I do here? I can't. Goodness, I'm making silly math mistakes. Okay. Notice what our reduced polynomial is. And we have to, if we can factor it, we can factor it. But this one also can't be factored. I need you to think about this a second. How many places did you see the graph on that graphing calculator? How many places did it cross or bounce at the x-axis? It's just that one place, but that's a multiplicity of 2 because it was a bounce, right? We need 2 more solutions. They're obviously not real solutions, or we would see them somewhere on the x-axis. So it's a pretty safe bet that we have to do quadratic formula because we need complex solutions for this. Does that, hopefully that kind of makes sense? Okay, so we're doing quadratic formula again. Opposite of b plus or minus square root of b squared minus 4ac all over 2a. I'm going to grab my paper here so that I'm not making careless mistakes, because I seem to be doing that. Okay. 16 minus 4 times 13 ends up being a negative 36. I'm going to skip that step, sorry, because I'm running out of room. So that gives us 6i all over 2.
Wouldn't it be a positive 4 though? Because negative 1 is negative
Where?
16 minus.
16 minus 4 times 13.
Okay.
So the 4 times 13 gives us, whatever, 70, no. I don't know. I'm brain freeze today. Well, 52. There we go. So 16 minus 52 is what we're doing there. Okay. This is going to simplify then to, we have common factor of 2, so this simplifies into, 2 goes into 4 2 times, plus or minus 3i all over 1. So our solutions then are this 2 plus 3i, 2 minus 3i, and then also 1. And to help myself out, and I would suggest you do the same thing, you may want to put a little note here. That's of multiplicity 2. That helps you realize, okay, this is 2 solutions, and this is 2 separate solutions. Altogether, we are getting the 4 that we say we need. Does that make sense? Okay. All right. Let's try another one of that type. That's why I asked you to get out that extra paper. I'm going to add another problem here for you guys to try. Similar type. Okay? A little. Here it is right here. This is the one I want you to do. This one's a little bit different. If you notice, it says find all of the solutions for this equation. You don't need your graphing calculator for this one, because notice I'm telling you 1 is a solution. So that means use 1, do your synthetic division, and then get your reduced polynomial and go from there. Okay, so try that one for yourself. Oh, right? Okay, so you're told what one of solutions is, so you're doing your synthetic division, you get this reduced polynomial. You're factoring. Make sure you're reading about what the format needs to be for your final answer. It's asking for solutions, so that means you want to do x equals. If it had asked for factors, then you would write it in this format here, right? The key, though, notice I put this in green to kind of highlight and remind you to include all of the solutions. You need to make sure you're including the x equals 1 that we were originally given. Okay, so please be conscious of that. If you would like, maybe just write that down on that paper if you want to try this one yourselves. This one is similar to the one the previous one that we saw on the calculator, where you get a bounce, and so you're going to divide twice. And then you can do your quadratic stuff. Okay, so you might not need the extra practice. You're going to get quite a bit of practice. There are 2 different things that I want you guys to do, and you've got time to get started now, so you can kind of ask questions of me and get help from neighbor, okay? So there's a My Math Lab, and that's due by day 1 of this next week. And then there is also a quizzes activity also. It should be working. It was not working earlier, but it should be set to be working now. So one quick note about the My Math Lab. I already had somebody coming and asking questions on that. They were wanting to get some extra help on it. When she was writing her answers for the possible rational zeros, she put -1 and then +1, -2 and then +2, and so on. My Math Lab marked it wrong, so I'm going to go back and check for that type of thing on the answers. I don't know why, but it's looking for you to give the positive and then the negative. So just kind of be conscious of that when you're working on the My Math Lab, okay?